Welcome back to Physics IB. Today we're going to do B2, so the greenhouse effect, and we're going to cover emissivity, albedo, and the solar constant as well. Starting off with emissivity. If you know what black bodies are, you will also know that they don't exist. So we can use emissivity as a way of comparing the power radiated by a real-life object with the power radiated by a black body object, and it's just a ratio of the two. You can also calculate it with the equation in the formula data booklet, which is power radiated per unit area over the Stefan Boltzmann constant, which is 5.67 times 10 to the minus 8, and multiplying that by the temperature to the power of 4. We also have the albedo, so this is the total scattered power over the total incident power on an object. We can use this to look at geographical aspects of the planet, potentially. So different materials have different albedo values. So snow and ice have much higher ones, meaning they scatter a lot more power than others. For example, water, forests, or deserts. And it can be seen to affect the temperatures in the North and South poles, lowering them more than in the equator, for example. The solar constant is the average intensity of electromagnetic radiation on the Earth's outer atmosphere. It's of 1 square meter in 1 second, and it's also equal to the average apparent brightness. So I'm going to draw a very quick diagram here of the sun, because we're going to work out the solar constant. So we've got the sun and we've got the earth here. I'm just going to fill that in because it's too small. And we can see that the sun emits electromagnetic radiation in all directions, and we can assume it's a spherical release of energy and radiation. So that sphere is going to then reach the Earth like this. So we're just going to draw a very rough circle to represent this sphere. And the distance between these, the sun and the earth, and therefore the more or less the radius of this sphere, would be the distance between the sun and the earth, which I googled, is about 1.55 times 10 to the 11. So I'm going to then take the equation for apparent brightness here, which is power over 4 pi d squared. We can see here 4 pi d squared is the same as the equation of surface area of a sphere, if we think that d is the radius. So in this case, d, as we've said, is 1.5 times 10 to the 11, so that's what I've put in here on the bottom. And I also did a very quick Google search of the power emitted by the sun, which is 3.8 times 10 to the 26 watts. If you plug that into the calculator, you get approximately 1,340 watts per square meter. And I thought it was a pretty good estimation, considering then in the data booklet it says it's around 1,360. So considering the rounding errors, I think that's pretty good. Moving on then to the greenhouse effect, which is the whole point of the video. You probably know what it is, or at least have heard of it, since it's very current in the media and very much talked about. So we have the sun here mainly emitting EM radiation, and it reaches the earth, as we discussed on the previous slide. And this is mainly visible light, is then absorbed by the earth, and is then re-emitted here mainly as infrared radiation. Now, in the atmosphere, you might know the composition of it. It's mainly nitrogen, around 78% nitrogen. But then there's also other gases, so carbon dioxide is one, and then there's also methane, and I'll talk about those more very soon. But these gases in the atmosphere, CO2 and CH4 and other greenhouse gases, because of their natural frequency of vibration, they absorb infrared radiation, and this causes resonance in the bonds, which then makes more infrared being re-emitted into the atmosphere and back to the Earth. You can also look at it in terms of discrete energy levels. So, for example, nitrogen doesn't have a discrete energy level that matches the wavelength or the frequency of infrared, so it's not susceptible and therefore doesn't act as a greenhouse gas. But the other ones, so CO2, CH4, and so on, their discrete energy levels match infrared, and this can excite them, and then when they de-excite, then more infrared is re-emitted in all directions in the atmosphere and also back to the Earth. So this means that less infrared and EM radiation is going to space and escaping the Earth, and this warms the atmosphere and the Earth, and this natural greenhouse effect is actually what has made life on Earth possible. So it is very good. So more about the gases that cause this effect. We have CO2, which is what most legislation targets. It's naturally in the atmosphere from animal respiration. So, for example, every time you breathe out some carbon dioxide as a byproduct from respiration, and is naturally then absorbed by plants while they're doing photosynthesis. However, in recent times, or since the Industrial Revolution, a lot of carbon dioxide has been emitted into the atmosphere as well, alongside the natural stuff going on, through combustion of fossil fuels, cutting down of trees and everything. And that has really created an enhanced greenhouse effect. Another very common one is methane, CH4. It's released naturally in wetlands, in processes, and then is absorbed by more processes in soil and the atmosphere. But in addition to that, again, people in their farming have a lot of cows, and these cows, very hilariously, but not so much, they fart a lot and release a lot of methane into the atmosphere, and that is actually having an impact on the climate. Then we have water vapor, which is pretty self-explanatory. It's part of the water cycle. And then we have nitrous oxide, so N2O. This is released and then absorbed naturally by bacteria and several processes, but is then produced by us through combustion and the use of fertilizers. So that was about it for the greenhouse effect. I hope you enjoyed the video. If you have any questions, feel free to leave a comment and we'll get back to you. Otherwise, I hope you have a great day.